I think we have one last session before breaking. So Nagi is going to talk about some volume averaging theory. Nagi, are you there?
Yeah.
And can you share your screen? Just want to mention that Nagi has been the driving force behind all this. He's also the person that keeps us on track. That everything we are doing has as a solid physical foundation and theoretical foundation. So is going to try to convey that in a few slides, and that also serves as introduction for some of the effective material properties that Joseph will show later. Over to you, Nagi.
Oh, thank you, Francesco. That was awesome. You guys are doing an outstanding job. Let's see. So what I'm going to cover is the theory of simulation at the large scale. So it's going to be a very brief theory review. I'm not going to go into more details than just a simple example, the simplest example I could think of. But the idea there is we're not going to be able to simulate. Can you see my cursor?
Yes.
So we're not going to be able to simulate materials at this scale and at the same time simulate the material at an engineering scale. In our case, it would be going from 10 microns or sub 10 microns, let's say, from 1 micron to meters. It would be impossible to do that in 3D. And so the idea in the simulation at a large scale is to average, is to derive the equations at the macro scale from the equation at the micro scale. So this is a very formal way to derive the governing equations at this scale, given the governing equations at the micro scale. And so, what this lecture is all about is the process of deriving the governing equations at the macro scale. And so there are many books on this. The main ones are the book by Whittaker and the book by Horner. The book by Whittaker covers the method of volume averaging. The one by Horner talks about homogenization. One is upscaling by averaging. The other one is a highly mathematical way of rescaling your coordinates. I will not go into details of what those books are covering, but they cover a pretty wide range of topics. So what I'm going to cover today is a very simple case where we're interested in the deriving the effective heat conductivity of a material. Let's say that we have this material that you have seen before, and I just took a small section of it, and so with this material we define omega f, which is the domain that the fibers are occupying. So the domain omega f is not a contiguous domain, but it is really the sum of the domains of where all the fibers are. Sigma f is the surface of your domain. So this is you have to think more now in terms of a discrete domain where you go from a domain defined in the R cube space into a domain that's defined only where the fibers are. So the governing equations at the micro scale would be, and if these fibers are sitting in vacuum, there is no governing equations outside. But the governing equations at the micro scale are that the divergence of the heat flux is equal to 0. And with a boundary condition, the heat flux at the boundary of the fibers is equal to 0. In other words, the heat in this case can propagate only along the fiber direction. So again, this is the only case that I'm going to cover in upscaling, in derivation of the upscaling equations. So the first thing that you want to do is since we're not going to be solving at the micro scale, what we will be solving will be an average along the continuous domain. So the way we're going to do that is we're going to do a running average. So at every X location, we define an averaging a volume. And usually people, for homogeneous materials, they call that the representative elementary volume. In our case, we don't, it can be any volume. In this case, it'll be just the volume we're going to filter or average over. And so if we define the average of a function to be the running average, which will be the average from minus delta 2 to plus delta 2 and divided by the averaging length of f of x plus xc. So you're sitting at x and you're averaging along xc, the xc domain that covers the entire averaging volume. And when you go outside, you're not defining anything outside. So what this does, it does well. Before I go into this, right now I just want to define extending the running average from integrating from minus delta over 2 to plus delta over 2 to integrating from minus infinity to plus infinity. In order for us to be able to do that, we define a filter function, which will be 1 from minus delta over 2 to delta over 2, and be 0 outside that range. So in this case, now we can, the average of a function is 1 over delta integral from minus infinity to plus infinity of f of c plus delta times c plus zeta times g of zeta d zeta. So you can see that because g of zeta is 0 outside minus delta over 2, so it goes, the minus infinity goes to minus delta over 2. And then so you can see that these are equivalent, except this allowed us to go from a limited domain to an infinite domain. And if you do a change of variable, you can see that this is nothing but the convolution integral for a filter function. In this case, it's just defined to be 0 outside minus delta over 2 to 1 to 0 outside delta over 2. So essentially what this allowed us to go from the formula that Whittaker uses in terms of running average to a formula that is actually a convolution integral. So this is the first step in deriving equations. Now, one thing about the filter that we have chosen, it has compact support, that is at the boundary of the domain, G is equal to 0. So here you can see G is equal to 0 at delta over 2. So in other words, we don't, the filter is 0 at the boundary of our domain, of our averaging domain. Another property of that filter is that it's an even function. So now if we average the gradient, so we defined here the averaging of a function. We're going to define the averaging of a gradient. So anytime you have the governing equations, you end up with gradients that you need to average. And so this is what we're going to cover here. And we're going to only talk about averaging the gradient, but you can other operators, you can follow the same thinking. So now if you average a gradient of f, you get 1 over delta on the integral of the gradient of f done at a gradient with respect to c of g of c minus x dx. Now, because it's a compact support, and because this is the volume integral of a gradient, you end up with the integral over the surface of your domain. But because the g is 0 at sigma, this goes to 0. And you end up with minus 1 over delta, the integral of f times the gradient of g with respect to c. Now, because g is an even function, the gradient with respect to c is equal to minus the gradient with respect to x. And therefore, now we are integrating grad x. So we can pull it outside the integral with a minus sign change. So we end up with the gradient with respect to x of the filtered function. So with this prove that the average of a gradient is equal to the gradient of the average. Now you can apply that to your governing equations throughout without having to think about it. Now, the other thing that we need to do, and this is a little bit tricky, is if you remember what I just said, is our computational domain at the micro scale is only the domain that's occupied by the fibers, including their surface. So our domain is omega f union of the surface. And so it's not defined in R cube, but it's defined only in the volume occupied by the fibers. So in order for us to be able to integrate over the entire space, we need to go from omega f union sigma f to the R cube domain. And so in R, we define Q to be Q, which is equal to QF in the micro scale domain, and Q to be 0 otherwise. So this allowed us to go from a non-continuous domain defined by omega f to R cube essentially, to the entire space. And so if we introduce an intermittency function, which will be 1 in the volume of the fibers and its surfaces, and to be 0 otherwise, then our continuous function that's defined in R cube is now gamma of xi, qf of xi, for all xi in R cube. So you can see that now we went from qf defined only in the volume of the fibers to q super f, which is defined everywhere in R cube. So now you can do the same thing for extending the gradient, and you extend the gradient by multiplying the gradient by gamma f. And so if you multiply the gradient by gamma f, and you can do differentiation by part, you can see that del dot xi of gamma f qf is equal to gamma f grad xi dot qf plus a qf times the grad of the intermittency. But remember, the intermittency is a step function. So in other words, our intermittency is a top hat function. Its gradient is actually the delta function. So its gradient is infinite. So we end up with, by extending our gradient from omega f union sigma f to R cube, we went from a well-defined gradient to a gradient that is defined in R cube plus a q at the surface times an infinite function. This is a delta. Remember, the integral, the gradient of a step function is actually the delta function. The delta function is defined is infinite at xi equal to xf, but its integral is equal to 1. So now if we volume average our function, and we can do the volume average because now we have defined the function in R cube. So if you volume average that, you get again the fact that the gradient of qf is equal to the gradient with respect to x plus the integral of that comes from integrating the delta function, multiplying the delta function by g and integrating, you end up with the integral over the surface of your fibers. But because of our boundary condition, qf is 0 at the interface. In this case, this particular case, this term drops out. So essentially, we have shown that the governing equations at the large scales are actually del dot at the large scale of the average q equal to 0. So in other words, we did preserve the heat conduction that that the divergence of the average heat flux is equal to 0. And so now the question is, how are you going to, how do you represent this? Well, we're going to use fixed model for the heat flux. And we say that the average heat flux is equal to a conductivity, a 3D. Now, don't forget that in this case, the conductivity is a tensor, because if you look at the heat flux along the fibers and you average them, you can see that in some cases the heat flux is this way, in some cases the heat flux is this way. In general, the heat flux is at an angle, even though your gradient is along one direction. And so, essentially, in order for you to compute the effective conductivity of our averaging volume, what you do is you compute the governing equations at the micro scale, and this is what PuMA does. By imposing the temperature gradient in one direction, then you impose it in the second direction, and you impose it in the third direction. By doing that, it gives you the entire flux with respect to a gradient in one direction, plus the flux with respect to gradient to the third direction, plus the flux with respect to gradient in the second direction. And so, so you'll be able to invert Q by computing the effective conductivity. So this is essentially the motivation between computing effective properties. You compute the effective properties because of the fact that the heat conduction equation is also satisfied for the particular case of the fibers sitting in vacuum. Don't forget that we have neglected an important term, which was the surface integral. For cases where we have two materials, this becomes a lot more complicated. But you end up with the same equations, except that when you sum the two equations, this term cancels out. But I'm not going to go into that detail. I think this is where we're going to stop to gain some time in our schedule.